Welcome you all in my next lecture. So, this lecture my plan is to talk about mixed derivative theorem. In fact, I already discussed for a functions f from Rn to Rm the notion of partial derivative, directional derivative and total derivative. And when I was discussing about partial derivatives, then there are kind of certain things like mixed derivatives. If you remember, in my last lecture I have discussed, and this lecture also I will start on that there is a notion of mixed derivative, and then there is a corresponding theorem, mixed derivative theorem, that I will discuss. Along with I will talk about mean value theorem, then the notion of Hessian, then Taylor's theorem for functions of two variables, and then as an applications linear approximations and increment estimation. So, that is the plan of my lecture. So, I will start with mixed derivative just to recall what do I mean by mixed derivative or partial derivatives, and then I will start with mixed derivative theorem. Okay. So, what is my outcome of this lecture? So, this is the tentative plan. Okay. So, I will start with a function f, again scalar field, real valued functions of variable from Rn. Okay, it is a functions from Rn to R, or in fact some open subset A subset of Rn to R. So, what are the results or concepts I am trying to discuss is that higher order partial derivatives. I already introduced the notion of partial derivatives. Again, I will just start with once again just to recall the higher order derivatives. Then of course, mixed derivative will come, and then I will give an example of a function for which mixed partial derivatives are not equal. I will give an example, and of course, I will introduce the notion of mixed derivatives that I think I have introduced in my earlier lecture as well. And then I will talk about one example where you will see that mixed derivatives, they are not equal at some point. So, the questions that when I can say that the mixed partial derivatives or mixed derivatives when they are equal, yeah, there are some certain sufficient conditions that also I will talk about when mixed partial derivatives are equal. I will give some sufficient conditions and show that yes, if this is true, then I can talk about that mixed derivatives are equal. And then I will talk about, or I will give the notions of Hessian matrix. In fact, it has something to do with the second derivative of my functions f. I will talk about that. And then I will talk about mean value theorem. Like in the real valued functions of real variable, you are familiar with the concept of mean value theorem. So, in case of vector valued functions of vector variable, or say real valued functions of vector variable, that means scalar field, is there any notions of mean value theorem? So, here you will see there is a theorem, but rather you will have mean value inequalities that we will see. And we will have also, I will talk about the extended mean value theorem. Of course, when I will talk about that, then you will see what do I mean with that mean value theorem in this context, along with extended mean value theorem. And finally, I will talk about Taylor's theorem. So, like Taylor's theorems, you know, for real valued functions of real variable. Since I have introduced the notions of derivative from vector valued functions of vector variable, so or in particular the scalar field, do I have a notions of Taylor's theorem, and if there is any, then what will be the corresponding statement, and is there any applications for that. So, that is the kind of tentative plan for this lecture. Okay. As I said, I just recall the notions of partial derivatives I already introduced in my earlier lectures. Let me just recall once again to talk about that mixed derivative theorem. So, what I am doing is that, so let f be a function from some open subset of Rn to R. Okay. So, if suppose the partial derivative exists, suppose if I have a functions from Rn to R or some open subset S of Rn to R, then you know, since it is Rn, that means n many coordinate axis directions are there, or you have a orthonormal basis consisting of n linearly independent vectors, then I can talk about the partial derivative of f with respect to n many variables, right, x1, x2 up to xn. So, that means del f, suppose partial derivative exists first order, that means del f del x1, del f del x2. So, these are the object exist. So, del f del xi suppose exist, okay, for I is equal to 1 up to n. Then what I am doing is that I am introducing a notion which is called del 2f del xj del xi. That means what I am doing, I am just first doing or considering the partial derivative of f with respect to xi variable, and then I am taking, so once I have a function f from Rn to R, then you can easily see del f del xi okay, it is also a function from Rn to R. So, if f is a function from set S subset of Rn to R, then del f, suppose del f del xi exists, okay, then this is also a function from S subset of Rn to R. What is that map? Just this is nothing but x naught goes to del f del xi at the point x naught. Given a function's f from Rn to R, each partial derivatives I can think about again a map from set S subset of Rn to R. Since it is again a first order partial derivative is a function from Rn to R, then again I can talk about the partial derivative of that functions with respect to again n many variables. So, therefore, so once the suppose del f del xi exists, now I can think about it is a functions from Rn to R. So, therefore, the partial derivative with respect to another variable xj makes sense because it is a function from Rn to R, and suppose that partial derivative exists. So, that means I can take the partial derivative of del f del xi, then I am denoting as dijf or f of suffix xi xj, that is same as del ijf or del xi del xj. Now, look at the notations what I am doing. So, it says that okay. So, what are, look dij, d capital D suffix ij, that means see the variable I is near to d. So, that means I am first what I have to do, I have to just do the partial derivative of f with respect to xi variable first, and then I will take the partial derivative of del f del xi with respect to the jth variable. So, that is why if I is near to d, take the partial derivative of f with respect to that variable. Once you are done, then take the next variable partial derivative of the function del f del xi. Similarly, here also f suffix xi xj, xi is near to f. So, that means first you consider the partial derivative of f with respect to xi variable. Think about the functions del f del xi is a map from Rn to R. Then you consider the partial derivative of del f del xi with respect to the jth variable. So, this is this how the notation comes. So, next one for example del q, that means, so look at notation. So, what I am doing, so I am saying that del q f del xk del xj del xi. What does it mean? So, that means first you perform the partial derivative with respect to xi variable. Think about it is a map from Rn to R. So, therefore, I can talk about the partial derivative with respect to xj variable of these functions. Suppose this is exist, again once this is again a function from Rn to R. So, therefore, I can talk about again partial derivative of this function with respect to some variable xk. So, this means take del f del xi, think about it is a function from Rn to R, perform the partial derivative with respect to xj variable, again it will be a function from Rn to R, then perform the partial derivatives with respect to xk variable. If these things happen, then I will just take a notation, this is d suffix I j k f. I is very near to d, that means first you perform the partial derivative of f with respect to xi variable, then talk about the partial derivative with respect to xj variable, but of the functions del f del xi. Okay? And finally, you have to perform the partial derivative with respect to xk variable, but which functions? Del to f del xj del xi, that functions. Okay. So, this is the corresponding notation f suffix xi xj xk, that means first you perform with respect to xi variable of the functions f, then you perform the partial derivative with respect to xj variable of the function del f del xi, and finally you perform the partial derivative with respect to xk variable of the function del to f del xi del xj. So, that is how the notation, this is for 2 and 3, and also this will like that. I have put a note here. So, what is the note? So, in the notation dijkf, I already mentioned the index I which is close to d is first and then next index j and so on. In other words, the notation f suffix xi xj xk, the variable xi which is close to f is first and then next variable xj and so on and so forth. So, that is how. So, that means just look at the notations, look at the suffix symbols. If I j k, if I is appears whichever variable I j k does not matter, if it appears near to d, you perform the partial derivative of your function with respect to that variable first, and then you can go to the next one. So, then you have to perform the partial derivative with respect to that variable, but remember you have to take the partial derivative of the functions del f del xi. Okay? And so on and so forth. If you go for the third one, then means you have to perform the partial derivative with respect to third variable, but of the functions del to f del xi del xj. So, that is how the sequence goes. Now, this is the notions of mixed partial derivatives, again I already introduced. So, it is that the partial derivatives dij, see look the symbols d suffix ij and d suffix ji. So, that means first one is what? First one is that I am taking the partial derivative of my functions with respect to xi variable first, and then I am considering the partial derivative of my function del f del xi with respect to xj variable. And what about the second one? I am considering the partial derivative of my function with respect to xj variable first, and then I am talking the partial derivative of the variable xi of the function del f del xj. So, that means this is nothing but, if I say this is del f del xi you do first and then del xj. And what about this one? You perform del f del xj first and think about this as a functions from Rn to R, perform the partial derivative with respect to xi variable. Now, the question is when these two are equals. So, that means does not matter whether I am doing performing the partial derivative first ith variable then jth variable or first jth variable then ith variable. So, these are called mixed partial derivatives. I will show an example that in general this is not equal. However, if I put some sufficient conditions, then these two are equal. Look, so I have given an example, okay, again just to have the notation, give the proper meaning of the notations, okay. So, let f, say I am just very special case I am talking about here. So, let f be a functions from set A subset of R2 to R, be a scalar field, in fact this is defined by f of x y is equal to z. Let A be is an interior point of S. For a functions of two variables, so how many second order partial derivatives we will have? Since it is a function of two variable, so therefore I can have two first order partial derivatives del f del x and del f del y, right. These are first order partial derivatives, and while I will talk about the second order partial derivatives. So, each del f del x and del f del y I can think about is a functions from again S subset of R2 to R. So, del f del x again I can perform the partial derivative with respect to xy, that means del 2f del x square, del 2f del y del x. Similarly, del f del y I also think about as a function from a subset of R2 to R. Also, I can perform two partial derivative with respect to xy variable. That means again I can talk about del 2f del x del y and del 2f del y square. So, that means 4 second order partial derivatives will be there. So, I have actually listed down. So, there are 4 second order partial derivatives which are given by. So, first this is the notations. So, d11 at AB, which is nothing but dxx of f at AB, which is f of xx at AB, which is del 2f del x. These are notations. So, look at this is the best way to understand. What I am doing is that first I am performing the partial derivative of f with respect to x variable. Okay. Then I am thinking about these functions from R2 to R and then perform the partial derivative at the point AB. And this is I have written. So, this is the definition of partial derivative with respect to x variable of the function del f del x. So, that means what you do, you consider the limit h approaches to 0 fx. So, this is nothing but del f del x. So, this is the notation del f del x. Okay. So, at the point a plus h comma b minus del f del x at the point a b divided by h. So, that means first you perform the partial derivative of f with respect to x variable, think about is a functions from a subset of R2 to R and then perform the partial derivative with respect to x variable, and this is the definitions. If this limit exists, then I will say that dxxf at the point a b or fxx at the point a b or del 2f del x square at the point a b exist. What about the second one? Again just look at the suffix notation, that it will be very clear. So, that means what? dyx. So, that means first you perform the partial derivative with respect to y variable and then perform x. Similarly here, first you perform the variable with respect to x first and then perform y. Okay. So, I think this should be xy. Yeah, I think there is a mismatch if I do correctly. So, first x. So, that means I think this should be, yeah. So, look. So, first I am doing with respect to x first and then y. That means this is, that is fine. The y, that means this should be yx first. Now, this is okay. So, x first x then y, first x then y. So, I think this should be xy. So, first perform with respect to x variable and then y. So, that means this should be I think 1 comma 2. Okay. So, that is the notation. So, which is very near to f x. So, that means first perform the partial derivative with respect to x variable and then y. Similarly, here x is near to d, first perform with x and then y. Again, so that means this is the best way to understand this symbol. That means first you perform the partial derivative with respect to x variable and then perform the partial derivative with respect to y variable. And what is the definition? This is the definition. Limit k approaches to 0, del f del x at a comma b plus k minus f of x a b divided by k. Okay. Other two will be there again. So, this is the one. So, yes. So, this is I think correct. This is first you perform with respect to y variable first and then x. So, that means this should be 1 2, that's correct, and this should be 1 2, this is correct. Correct, this is 1. So, first no, I think this is again this should be, yeah, this should be yx. First perform with respect to y variable, y is near to d and then x. Okay. So, this is the one of the way you can easily understand. First you perform the partial derivative of f with respect to y variable, then think about is a functions from R2 to R and then perform del x. So, that means this is limit h approaches to 0, del f del y at a plus h comma b minus f y a b divided by h. And the fourth one, there is both variable y is there. So, dt2 dyy dfyyb. So, that means perform df dy and then take the partial derivative with respect to y variable. So, and this is the corresponding definitions. So, that means if I have a function from R2 to R, then there are 4 second order partial derivatives are there. What are this? What are those? So, first one is del 2f del x square, second one is del 2f del y square, then third one is del 2f del y del x, and fourth one is del 2f del x del y. Okay. So, one example I have given. So, suppose you have a functions f x y which is x cube plus x square y cube minus 2y square for all x y. Then first order partial derivatives are given by. So, that is very easy, right? What I already said, that to perform the partial derivative with respect to x variable, what you will do? You just think about y as a constant. Okay. Keep y is a fixed or constant, think about is a function of single variable and perform the derivative with respect to x. So, here also function is given, think y is a constant and perform the derivative with respect to x variable. Then what will happen? This should be 3x square and this should be 2xy cube and y is constant. So, derivative of y square with respect to x variable is 0. Similarly, you can easily calculate del f del y. So, now you have a functions fx del f del x and del f del y, then I can perform the second order partial derivatives. So, that means since it is a, again it is a functions from R2 to R. So, these are functions from R to R, right. So, fx is a functions from again R2 to R. Okay. How it is defined? Fx at the point xy which is nothing but 3x square plus 2x y cube. Okay. Now, since it is a functions from R to R, then you can perform the again the partial derivative with respect to x and with respect to y. If I perform the with respect to x, this is fxx which is nothing but 6x plus 2y cube keeping y constant. And what will happen f of xy, you see, first I perform fx, then perform with respect to y variable. If I perform with respect to y variable, then what will happen? This is goes to 0, 3x, x is constant with respect to y variable, I am performing the partial derivatives. So, what will happen? It should be 3 into 2, that means 6xy square and this is nothing but 6xy square. And similarly, fy also you can, it's a map, right. Fy is again a functions from R2 to R, and what is my fy at the point xy, which is nothing but 3x square y square minus 4y. Okay. Then perform the partial derivative with respect to y variable and with respect to x variable. So, that means 4 second order partial derivatives will be there for this function. And this function is very nice, it is a polynomial in x and y. So, all partial derivative exist, okay, first order, second order, in fact higher order as well. Okay, so one example I have given, as I said that I want to talk about the equality of mixed partial derivatives. So, that means suppose you have a given a functions f and suppose dij or dji of your functions at the point x not exist. Now, the question is when their value will be equal or not. So, one example I have given, example of such function where your mixed partial derivatives are not equal. What does it mean? That means you perform the partial derivative or calculate the partial derivative of f with respect to I variable first and then j, and first j then I, and evaluated at the point, then they are not equal. So, for example, this is the functions f of xy which is xy times x square minus y square divided by x square plus y square if xy is non-zero, and 0 if xy is equal to 0. So, this function is again very nice functions except the point 0 0, because this is the breaking point. If xy is non-zero, this function is quotients of two polynomials in x and y. This is nice, it is partial derivative with respect to x with respect to y variable at a point xy exists, xy is non-zero. So only the breaking point is there. There you have to calculate explicitly what is the partial derivative of f with respect to x variable or y variable at the point 0, 0. There you will have the problem. There you will have to use the definitions. Okay. So what are the things I just said to check? First you check that whether f partial derivative of f with respect to x variable, partial derivative of f with respect to y variable, whether these are continuous functions on R2. F is a function from R2 to R, right? So if I again, I already said, if I have the consider the partial derivative of f with respect to x variable, again it is a function from R2 to R. Similarly, partial derivative of f with respect to y, again it is a function from R to R. So first you get those functions and then talk about the continuity. Acha. Second one is that, okay, once suppose first order partial derivative exists, then I can talk about the second order partial derivative, that means d1 to d2 1f. I said that, okay, this should exist at every point. One has to check, yes, for these functions, this mixed partial derivative also exists at every point on R2 and are continuous except at the point 0, 0. So, okay. So, again, so if I calculate d1 2 and d2 1, again it will be functions from R to R. So, this functions is defined from whole R2 to R. However, this function is not continuous at the point 0, 0. So, that means again there will be a breakpoint and you can check that, okay, you have to prove it, this is not a continuous functions. Okay, I have again written. So, if the point xy is non-zero, then things are easy, right? Because if xy is non-zero, then you know your f, then you know your fx, you know your partial derivative of f with respect to x variable with respect to y variable. Again, if the point is non-zero, you can easily do that because the function is nice. The only point you will face, and that there you have to use the definitions of partial derivative, is the breaking point, I mean 0, 0. So, that's, I said explicitly you have to calculate the second order partial derivatives of f at the point 0, 0. If you evaluate it, it will be 1, and if consider the second order partial derivatives with respect to two variable first and then 1 at the point 0, 0, it is -1. That means I have written second order mixed partial derivatives, they are not equal at origin. However, if you are away or if you are differ from the origin point, then mixed partial derivative exists, as I already mentioned here. So, this is exist, okay, and they are equal. But except the point, but only the point origin, there you will have the difficulties where mixed partial derivative exists, but they are not equal. I think I have done something, yeah, okay, I have written little calculations here. Okay, look, so what I have done, consider the point xy is non-zero. If xy is non-zero, then what will be your f? This should be this function, right? Xy times x square minus y square divided by x square plus y square. Then you just perform the partial derivative of f with respect to x variable, keeping y constant, and keeping x constant, perform the derivative. This is a normal usual derivative that you are familiar with in the single variable case that you know. So, that means fx at the point xy, fy at the point xy, you can easily calculate if xy is non-zero. So, only part is remaining, as I said, because the function differs at the breakpoint 0, 0, you have to calculate, and there you have to use the definitions. So, I just use the definitions fx at the point 0, 0, which is limit h approaches to 0, f of h0 minus f 0, 0 divided by h, by f of 0, 0 it is given 0, f of h0, just look at the definitions f of h0. So, look, so since y is 0, so that means this y is 0, that means the function value is 0. So, therefore, this is 0 by 0, so then the value will be 0. Similarly, you can calculate fy at the point 0, 0. So, therefore, again do the same definitions, again it is 0. So, now your functions del f del x, it is defined on whole R2. At the point xy, if it is non-zero, its value is there, and at the point 0, 0, it is 0. Similarly, the partial derivative of f with respect to y variable, again it defines on whole R2, that means the partial derivative, first order partial derivative exists at each point. If xy is non-zero, this is the value, and if xy is 0, this is the. So, now it is a function from R2 to R. Again, you can talk about the mixed partial derivative, that means partial derivative with respect to x and y variable of the function del f del x. Similarly, partial derivative with respect to x and y variable of the function del f del y. Again, like the earlier one, you just replace f by del f del x and del f del y. The only part you have to concern the point where it is 0, because if it is non-zero, that is a very nice, it is again Look, this is a quotient of polynomials in x, y. So, you can easily calculate the second order partial derivatives at the point x, y if x, y is non-zero. Again, since the breakpoint is 0, 0, so you have to just use the definitions, print first definitions of existence of partial derivatives, and you have to calculate. So, that's I have exactly done. So, that means first so look, this is a symbol. First you have to have the partial derivative with respect to x variable, then you have to do partial derivative with respect to y variable of the function del f del x, and this is exactly the definition. Limit k approaches to 0, f of x 0 k, f of x 0 0 divided by k. Now f of x 0 0 I just calculated, it is 0, so not an issue. Now I have to check what is f of x 0 k, but 0 k is a non-zero point different from the origin. Now look at the definition. F of x at the point x, y it is given. So, it just evaluated at 0 k. If I evaluate at 0 k, then what will happen? 0 k, that means okay, what I am doing, it should be f x 0 k, or x is 0, sorry, x is 0, y k. So, x is 0 means this is term will not be there, this term will not be there, x is 0. So, only k part, so that means minus k 5, so minus k 5 will be there, and you have a denominator, x is 0, y is k, that means k to the power 4, that means this should be minus k to the power 5 divided by k to the 4. And f x at 0 0, I just said that this is 0, so that means what we will have, this will be limit k approaches to 0 minus k 5 divided by k 4 times k, that means k 5 get cancelled, that means we will have minus 1. So, that means to talk about the partial derivative or second order partial derivative of f suffix x y at the point 0 0, first you need to partial derivative of f with respect to x variable at each point, then only I can talk about the limit of the second order partial derivatives at the point, because I have to calculate the. So, unless and otherwise your first order partial derivative defines in a neighborhood of 0 0, I cannot talk about the second order partial derivatives. So, the first one is already kind of I convince you, yes, look, the first order partial derivative with respect to x variable and y variable, it is defined everywhere on R2, and therefore in particular in a neighborhood of 0 0. So, therefore I can talk about the mixed partial derivative or second order partial derivatives at the point 0 0. Similarly, look this one. So, what you have to do? So, first you have to consider the function del f del y, that means first you take the partial derivative with respect to y variable del f del y. So, think about is a function from R2 to R and perform the partial derivative with respect to x at 0 0. So, and this is exactly the definitions, limit h approaches to 0, f of y h0 minus f of y 0 0 divided by h, but f y at 0 0 I already calculated, this is 0. So, this is 0 value. And what will happen f of y at h0? Now, h0 is a point which is different from the origin, and this is exactly the calculations I have done. So, therefore, f of y at the point h0, that means y is 0, y is 0 means this term will not be there, this term will not be there. So, only this term will be there. So, that means h to the power 5 divided by again. So, this is h square, that means h to the 4, y is 0. So, therefore, divided by h, again it should be 1. So, therefore, what I observed is that in this example, the mixed partial derivatives f of x y and f of y x at the point 0 0, both of them are exist. However, they are not equal. This is at the point 0 0 I am talking about. You just check that if the point is not 0 0, there the point value becomes equal. That is what exactly I have said, that check the both mixed partial derivative exists, but they are equal if your point is differ from origin. Okay. So, this I have done kind of little calculations, but still few parts are remaining. So, like you have to check the continuity. Now, you have in your hand what is your f, what is your partial derivative of f with respect to x, and what is your partial derivative with respect to y variable as a functions from R2 to R. Okay. So, now you can check the continuity. So, you have to check, since it is defined on whole R2 to R, then you can talk about the continuity. Of course, you can see you have to talk about the continuity in kind of since the functions breaks only at the point 0 0. So, you have to just check the continuity at the breaking point. Other point the function is nice, it is continuous, you can easily see, you can easily say. Okay. Again, and partial derivatives with this mixed partial derivative exists at every point R2, that is okay, that is again it follows from here. I am already just said that at 0 0 I already calculated, and it is minus 1 and plus 1, and f suffix x y and f suffix y x at any other point, that easily follows from this and this. So, not an issue. So, that means you will again all second order partial derivatives from R2 to R, then you can talk about the continuity. Again, you just see where is the break point and talk about the continuity on the break point, and other point you can just give some easy argument like cosines of two polynomials and something like that. Okay. So, therefore, I have talked about, I have given an example of a functions from R2 to R where your mixed partial derivatives exist at each point, and there is a point where they are equal and there are point where they are not equal. So the question is that, okay, if I have a functions f, suppose your all mixed or first order, second order partial derivative exist. Okay. So then when can I talk about then their value will be equal? Okay, because this example says that at some point they are equal, at some point they are not equal. So therefore the natural question is, can I give some restrictions on my say first order partial derivatives or say the second order partial derivatives, so that I can talk about whenever the mixed partial derivative exists they are equal. Like for example, sufficient conditions for differentiability. So we know that if my function is total differentiable or the total derivative exists, then we know that directional derivative or partial derivative exist. However, there are plenty of examples where your partial derivative exists, but your function is not differentiable, that means total derivative doesn't exist. So now the question is, can I put some extra conditions on the existence of partial derivative so that I can talk about the total derivative? And answer, you know that if the partial derivative exists and they are continuous, then you can talk about the existence of total derivative. Similar kind of things you can see some theorems. There is one theorem that is called mixed derivatives theorem. That means suppose you have a functions and suppose mixed derivative exists, can I have some conditions so that I can talk about whenever the mixed partial derivative exists they are equal? So answer is yes. Look, this is my theorem when mixed partial derivatives are equal. So this is my theorem. So suppose you have a functions f from say Rn to R, okay, where S is an open set in Rn, okay, and let x naught be a point in S. So look, so what is my assumption? I am saying that dijf and djif exist. So that means mixed partial derivative exists in a neighborhood of x naught. See, I want to talk about later, so I will say that okay, it should be continuous. So to talk about the continuity, I need the existence of my mixed partial derivative in a neighborhood of x naught. Okay, so that's I assume that. So assume that mixed partial derivative exists in a neighborhood of the point x naught. Suppose I have a point x naught in a neighborhood of x naught. If the mixed partial derivative exists, not only that, if the mixed partial derivative are continuous, that is an extra assumptions, okay, then I can always say that yes, their value will be equal. So therefore, what is my theorem? It says that not only the existence of mixed partial derivatives will allow you to talk about the equality of their value, but it's needed the continuity, the sufficient conditions. That means I need two things. What are the things? First is that mixed partial derivative should exist in a neighborhood of the point x naught, because I need the continuity of mixed partial derivative at the point x naught. Once I talking about the continuity of the mixed partial derivative at x naught, so that means I need the existence of mixed partial derivative in a neighborhood of x naught. Otherwise, I cannot talk about the continuity, right? If I want to talk about the continuity of functions f at some point, I need that the function should be defined in a neighborhood of that point. Otherwise, I cannot talk about the continuity. Okay. So this is your theorem. It says that if I have a functions f from S subset of Rn to R, where S is an open set, if I have a point x naught, suppose mixed partial derivative exists, that means dij, dji, this exists, okay, in a neighborhood of x naughts. On top of that, if I assume that mixed partial derivatives, they are continuous at the point x naught, then I will say that yes, they are always equal. That is called mixed derivative theorem. So there is another, so following a weaker version of the theorem, this is due to Schwarz. So this is little bit strong. So there is a weaker theorem. Weaker theorem means what? Look at the statement, it will be clear. Suppose you have a functions f from R2 to R, okay. So then where S is an open set in Rn, okay, there is this will be Rn, I think, okay. So if I have a function f from Rn to R, some subset open set in Rn, and suppose you have a point x naught, y naught, okay, so that means it should be R2, yes, that means there is a mistake, typos, this should be 2, and this is fine. So if I have a function f from R2 to R, okay, S is an open set in R2, suppose take a point x naught in S, assume that, okay, what I am assuming, look, I am assuming that first order partial derivative of f with respect to x, first order partial derivative of f with respect to y, and one of the mixed derivatives, that means f suffix xy, that means first you perform del f del x and then consider the del y of del f del x. So if these three exist in a neighborhood of the point x naught, okay, so what I want, so look, so that's nice actually. So instead of earlier one, what? Earlier one, I want the existence of mixed partial derivatives in a neighborhood of x naught. So that means if I want to, or if I want the existence of mixed partial derivatives, that means of course the first order partial derivatives, that means del f del xi or del f del xi, that should also exist, right? then otherwise I cannot talk about the mixed second order partial derivative. First order partial derivative has to exist, then only I can talk about second order partial derivative. When I am talking about the existence of mixed partial derivative, that means it is automatic that the first order partial derivative exists. Okay. But in the second one, I want that, okay, first order partial derivative exists along with one of the mixed partial derivative exists. I do not want the second one, that means f suffix yx, I did not say anything about that. Assume that fx, fy, f of suffix xy exists in the neighborhood of the point x naught, and not only that, f of f suffix xy exists, if it is continuous at the point x naught, then it implies that your other mixed partial derivatives f yx exist and their value will be equal. So that is why this is much more weaker. In a sense, I need the existence of first order partial derivatives and one of the mixed partial derivatives. Along with, of course, the mixed partial derivatives, I am talking about the existence, I need the continuity as well. If I have that one, then it automatically implies the existence of other mixed partial derivatives at the point. Moreover, this value will be same. So that is why this is weaker. So first ones, I need the existence of all first order partial derivatives along with all second order partial derivatives. Moreover, I need the continuity. Then only I can talk about the equality of the mixed partial derivatives. In the second one, it says that, well, I need the existence of first order partial derivatives along with one of the mixed partial derivative exists with and exists, not only exists, it should also continuous. Then the other mixed partial derivative exists at that point and their value will be equal. Okay. So that is called mixed derivative theorem. Maybe I think in my next lecture I will talk about, I will give some examples. Okay, this is the sufficient conditions, right? That means if the mixed partial derivative exists and continuous, then their value equal. So now the question is, suppose mixed partial derivative exists and suppose they are not continuous, then can I say that the value will always be not equal? Answer is no, you cannot say. May or may not. That means I will give you an example of a functions where mixed partial derivative exist, but they are not continuous. But two examples, one example I will show that the mixed partial derivatives at the point, value at the point, they are equal, and one example you will see mixed partial derivative exists, but they are not continuous, however, the value will be same. So that means if it is continuous mixed partial derivative, then of course value will be same. However, suppose the mixed partial derivative exists and they are not continuous, then there are two cases, either they should be equal or they should be not equal. So that in my next lecture I will talk about, I will give two examples where I will show that, look, this is the mixed partial derivative exists, however these are not continuous, but in some cases the value of the mixed partial derivative at a point equal, and in some cases the value of the mixed partial derivatives at a point not equal. I think I should stop here. Thank you.